The confirmation of 3I/Atlas as an interstellar comet marks another milestone in humanity's growing ability to detect and study objects that originate beyond our own solar system. Interstellar objects are cosmic messengers, formed around distant stars and ejected into the vast interstellar medium long before our sun and planets ever encountered them. The designation 3I itself is historically significant, as it indicates that this is only the third confirmed interstellar visitor ever observed passing through our solar system, following the enigmatic 1I/Oumuamua in 2017 and the more traditionally comet-like 2I/Borisov in 2019. Each of these discoveries has expanded scientific understanding and reshaped expectations about what kinds of objects travel between stars. And 3I/Atlas now joins this exclusive and scientifically priceless category. The object was first detected on July 1, 2025, by the Asteroid Terrestrial Impact Last Alert System, commonly known as ATLAS. The discovery was made using the ATLAS Survey Telescope located in Rio Hurtado, Chile, a site chosen for its clear skies and excellent conditions for scanning large portions of the sky. ATLAS is designed to rapidly identify moving objects, particularly near-Earth asteroids that could pose potential hazards. But its wide field capability also makes it exceptionally effective at spotting unusual visitors, like interstellar objects. Almost immediately after detection, astronomers noticed that 3I/Atlas followed an unusual trajectory that could not be explained by a bound orbit around the Sun. Its speed and hyperbolic path indicated that it was not gravitationally tied to our solar system, triggering rapid follow-up observations from observatories around the world. As additional data were collected, the object's interstellar origin became increasingly clear. Calculations of its incoming velocity showed that it was traveling too fast to have originated within the solar system, even if it had been gravitationally perturbed by the giant planets. Instead, its motion suggested that it had spent millions or even billions of years drifting through interstellar space before passing close enough to the Sun to become detectable. This realization placed 3I/Atlas in the same rare category as Oumuamua and Borisov, though with its own distinct characteristics that make it a unique subject to study. In addition to its interstellar designation, the object also carries the name C/2025 N1 Atlas, which follows the International Astronomical Union's standard comet naming convention. Under this system, the C/ prefix indicates a non-periodic comet, meaning it does not have a closed, repeating orbit around the Sun. The 2025 N1 portion identifies the year and half-month of discovery, along with its sequence among discoveries during that time. While 3I/Atlas emphasizes the object's interstellar status, C/2025 N1 Atlas places it neatly within the broader catalog of known comets, allowing astronomers to reference it consistently across databases and publications. What makes interstellar comets, like 3I/Atlas, so scientifically valuable is their status as natural samples from other planetary systems. Every comet that formed within our solar system shares a broadly similar chemical heritage, shaped by the same protoplanetary disk and influenced by the Sun's radiation and gravitational environment. In contrast, an interstellar comet formed around a different star, under different conditions of temperature, radiation, and chemical composition. When such an object passes through our solar system, it offers scientists a fleeting but extraordinary opportunity to study material that originated elsewhere in the galaxy, without the need for interstellar travel. These objects can provide insights into how common certain chemical compounds are across planetary systems, shedding light on whether the processes that shaped our own solar system are typical or unusual. For example, by analyzing the gases released as an interstellar comet warms near the Sun, astronomers can compare its composition to that of familiar solar system comets. Similarities suggest that comet formation processes may be broadly universal, while differences could reveal alternative pathways for planet and comet formation around other stars. In this sense, interstellar comets act as messengers, carrying information about distant star systems directly into our observational reach. The observational window for such studies is, however, extremely limited. Interstellar comets travel quickly, spending only a short time in the inner solar system before continuing on their long journeys through interstellar space. This makes rapid detection and coordinated observation critical. In the case of 3I/Atlas, astronomers mobilized a range of ground-based telescopes to monitor its behavior as it approached and then moved away from the Sun. Among the most notable follow-up observations were those conducted with the Gemini North Telescope, one of the world's premier optical and infrared observatories. On December 13th, researchers released new images taken by the Gemini North Telescope located on Mauna Kea, Hawaii. These observations were actually captured earlier on November 26, 2025, using the Gemini Multi-Object Spectrograph, or GMOS. The delay between observation and public release is typical, as data must be processed, analyzed, and verified before conclusions are shared. When the images were finally published, they immediately drew attention because they showed 3I/Atlas glowing with a distinctly greenish hue after re-emerging from behind the Sun. This greenish glow sparked widespread discussion, both within the scientific community and among the public. While the color might seem mysterious at first glance, astronomers quickly pointed to a well-known explanation: the presence of diatomic carbon, or C2, in the comet's coma. As a comet approaches the Sun, its ices begin to sublimate, releasing gas and dust that form a surrounding cloud known as the coma. When sunlight interacts with certain molecules in this coma, it can cause them to emit light at specific wavelengths. Diatomic carbon is particularly known for emitting green light when excited by solar radiation, a phenomenon observed in many comets native to our solar system. Importantly, the presence of C2 does not require any exotic or unusual chemistry. It is a common component in cometary comae and has been studied for decades. What makes the observations of 3I/Atlas especially intriguing is not simply that it displays a green glow, but that this represents a change from its earlier appearance. Previous Gemini observations had shown the comet with a noticeably redder coloration, suggesting a different balance of dust and gas emissions at that time. The shift toward a greener hue indicates that the comet's activity is evolving as it responds to increasing solar heating. Such changes are valuable clues to the physical and chemical structure of the comet's nucleus. As an interstellar comet heats up, different volatile compounds sublimate at different temperatures. More volatile ices may be released first, while others remain trapped until the comet experiences stronger solar radiation. The observed color change in 3I/Atlas suggests that new layers of material are becoming active, releasing different molecules into the coma. This layered response provides insight into how the comet is built and how its materials have been preserved during its long journey through interstellar space. Comparing these behaviors with those of solar system comets allows scientists to test broader theories of comet formation and evolution. If interstellar comets behave similarly to native comets when exposed to sunlight, it suggests that the fundamental physics and chemistry of icy bodies may be remarkably consistent across the galaxy. On the other hand, any significant differences could point to unique formation environments or evolutionary histories. In the case of 3I/Atlas, the presence of familiar molecules like C2 alongside observable changes in activity strengthens the idea that, while its origin is foreign, its behavior is not entirely alien. Beyond the immediate scientific findings, discovery